June 12, 1944. The Normandy beachhead, 6 days after D-Day. Hauptmann Klaus Bäumer of the German Army's Weapons Testing Office stood in a crater-pocked field near Villers-Bocage, examining what remained of an American M4 Sherman tank. The vehicle had taken a direct hit from an 88mm anti-tank round the weapon that had terrorized Allied armor since North Africa. But something was wrong with this kill. The penetration wasn't clean. The armor around the impact site had deformed in ways Bäumer had never seen before, absorbing energy that should have punched straight through. The weld seams, which typically cracked and separated under the shock of heavy impacts, remained intact. He ran his gloved hand across the fractured surface, feeling the texture of steel that had behaved differently. Back in Berlin, metallurgists at the Kummersdorf proving grounds had assured Wehrmacht leadership that American armor steel was inferior, straightforward, mass-produced material lacking the sophisticated alloys Germany employed. Yet here was physical evidence suggesting something had changed. The Americans, it seemed, had solved a metallurgical problem that German engineers hadn't realized needed solving, and they'd done it at industrial scale, on thousands of tanks, without anyone noticing until those tanks started surviving shots that should have destroyed them. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how American metallurgists transformed Sherman armor begins not in the fires of combat, but in the research laboratories and steel mills of the United States, where a revolution in armor plate manufacturing was unfolding even as the first Shermans rolled off production lines in 1942. American armor steel in early 1942 followed specifications inherited from World War I and refined during the interwar period. The standard specification, known as homogeneous armor plate, consisted primarily of iron with carbon content around 0.3%, plus small amounts of manganese, silicon, and other elements to improve hardness and toughness. This steel performed adequately against small-caliber weapons and shell fragments, but showed significant vulnerabilities when facing the new generation of German anti-tank weapons being deployed in North Africa. The German 88mm gun, originally designed as an anti-aircraft weapon, had proven devastatingly effective against Allied armor. Its high-velocity armor-piercing rounds could penetrate 3 inches of face-hardened armor at 1,000 yards, more than sufficient to defeat the frontal armor of early production Shermans, which ranged from 51mm on the hull front to 76mm on the gun mantlet. American ordnance officials reviewing combat reports from North Africa in late 1942 recognized a disturbing pattern. Sherman tanks were being knocked out at ranges where German tanks remained effectively immune to return fire. The problem wasn't primarily the gun, though the 75mm M3 certainly had limitations. The critical vulnerability was armor that couldn't withstand hits from weapons the Germans were deploying in increasing numbers. The Metallurgical Advisory Board on Armor Plate, established by the U.S. War Department in 1942, brought together specialists from steel companies, universities, and government laboratories to address armor performance issues. Among them was Dr. Edgar Bain, Director of Research at United States Steel Corporation, whose work on steel heat treatment and alloy development had established him as one of America's foremost metallurgists. Bain and his colleagues faced a complex challenge. Simply making armor thicker would increase tank weight beyond acceptable limits, reducing mobility, and increasing the load on powertrains already operating near their design limits. Adding more armor would also consume scarce materials and slow production at a time when manufacturing speed was critical. The solution had to come from improving the steel itself, making each millimeter of armor more effective at stopping projectiles. The physics of armor penetration were well understood by 1942. When a high-velocity projectile strikes armor plate, it creates enormous localized stresses that can exceed the material's strength, causing it either to fracture and allow penetration or to deform plastically while absorbing the projectile's kinetic energy. The outcome depends on multiple factors: the hardness and toughness of the armor steel, the angle of impact, the velocity and mass of the projectile, and crucially, the microstructure of the steel at the point of impact. Face-hardened armor, the standard for tank protection, used a surface layer of extremely hard steel to shatter or deflect projectiles, backed by softer, tougher steel that prevented the hard face from cracking completely through the plate. This combination, hardness to resist penetration, toughness to prevent catastrophic failure, represented the fundamental challenge of armor metallurgy. German armor steel of this period used chromium, molybdenum, and nickel as primary alloying elements, producing steel with excellent hardness and good toughness when properly heat-treated. But German specifications required tight tolerances and careful processing that slowed production and demanded high-quality inputs increasingly difficult to obtain as the war progressed. American metallurgists needed to develop steel that could be manufactured rapidly, with materials available in quantity, while matching or exceeding German armor performance. The breakthrough came from understanding not just what elements to add to steel, but how those elements affected the steel's microstructure under the extreme conditions of ballistic impact. Dr. Bain's research team at U.S. Steel, working in collaboration with metallurgists at Inland Steel, Bethlehem Steel, and the Naval Research Laboratory, discovered that certain combinations of alloying elements created microstructures that remained stable under shock loading, resisting the brittle fracture that allowed projectiles to penetrate. The key innovation involved increased nickel content, combined with specific ratios of chromium and molybdenum. Previous American armor specifications had limited nickel content due to supply concerns, nickel being a strategic material with competing demands from aircraft engines, naval vessels, and numerous other applications. But metallurgists demonstrated that increasing nickel from approximately 1.5% to 3.5%, while carefully balancing chromium and molybdenum additions, produced dramatic improvements in armor performance. This new steel, designated by various specifications that evolved through 1943, exhibited a property metallurgists termed high toughness at high hardness. Conventional armor steel became more brittle, as hardness increased a fundamental trade-off that limited how hard the face could be made, without risking catastrophic cracking. The new alloy maintained high toughness even when hardened to levels that would have made conventional steel unacceptably brittle. The manufacturing process for this improved armor required careful control at every stage. Steel mills had to maintain precise temperature profiles during rolling, ensuring the final plate thickness met specifications while developing the desired grain structure. Heat treatment, heating the steel to specific temperatures, then quenching in oil or water to harden it, followed by tempering to restore toughness, demanded precise control that some facilities struggled to achieve consistently. Republic Steel Corporation's plant in Massillon, Ohio, became a center of armor plate production using the new specifications. Engineers there developed processing techniques that could produce the improved armor at rates sufficient to support Sherman production schedules. By mid-1943, plates rolling off Republic's mills showed hardness, values reaching 300 Brinell, significantly harder than earlier production, while maintaining impact toughness that prevented brittle failure. Carnegie Illinois Steel Corporation, another major supplier, implemented similar improvements at its plants in Pittsburgh and Gary, Indiana. The collaboration between these competitors, sharing technical information through the Metallurgical Advisory Board, represented an unusual degree of cooperation driven by wartime necessity. Each company contributed research findings and processing innovations that collectively pushed American armor performance to levels that surprised even the metallurgists developing it. Testing of the improved armor took place at Aberdeen Proving Ground in Maryland, where ordnance engineers subjected sample plates to systematic firing trials using captured German weapons. The results, documented in classified reports through 1943 and 1944, showed significant improvements in resistance to 88mm rounds. Plates that would have been penetrated cleanly by earlier specifications now either defeated the rounds completely or produced partial penetrations that wouldn't have disabled the tank. The term illegal alloy, that later circulated in some accounts, though never an official designation, apparently originated from conversations among German metallurgists who examined captured American tanks and found alloy, compositions that didn't match any known American specifications they had on file from pre-war technical literature. From the German perspective, the Americans seemed to be using steel compositions that violated their own published standards, hence illegal in the sense of unauthorized or unexpected. In reality, there was nothing illegal about the new armor. The United States had simply developed improved specifications and implemented them across the production base without broadcasting the changes. Unlike Germany, which tended to introduce new tank models with great fanfare, American industry upgraded existing designs incrementally, improving components and materials continuously without creating entirely new vehicle types. The first Shermans to receive the improved armor came off production lines in late 1943. These vehicles, externally identical to earlier production, carried armor that was demonstrably superior in its ability to withstand hits from German anti-tank weapons. The changeover happened gradually, as steel mills completed the transition to new specifications and existing inventory of older plate was consumed. By early 1944, as production ramped up for the Normandy invasion, the majority of Shermans being shipped to Britain incorporated the improved armor. Crews receiving these tanks noticed no visible difference. The armor thickness remained unchanged. The tanks looked identical to earlier models. But the metallurgical changes meant these vehicles could survive encounters that would have destroyed their predecessors. The logistics of implementing this improvement across an entire production base demonstrated American industrial capabilities that Germany could not match. Multiple steel mills had to coordinate specification changes, modify processing procedures, and maintain quality control, all while increasing output to meet escalating demand. The automotive companies building Shermans, Ford, Chrysler, Fisher Body Division of General Motors, Pressed Steel Car Company, and others had to verify that the new armor met specifications and could be welded successfully using existing procedures. Welding represented a particular challenge with the improved armor. The higher alloy content made the steel more sensitive to welding parameters. Incorrect procedures could create brittle zones around welds that would crack under impact. Welding engineers developed new procedures and trained welders across multiple facilities, ensuring that the superior base metal wasn't compromised by poor fabrication. The American Welding Society, working with the Ordnance Department, published revised guidelines for welding high-alloy armor steel. These specifications required preheat before welding to prevent rapid cooling that could create brittle microstructures, specified particular electrode types, and defined inspection procedures to verify weld quality. Implementation of these procedures across dozens of manufacturing facilities producing Sherman hulls and turrets required coordination and training at a scale that reflected American industrial maturity. Quality control became increasingly sophisticated as production continued. Metallurgists developed rapid testing procedures that could verify armor, hardness, and composition without the lengthy analysis traditional methods required. Portable Brinell hardness testers allowed inspectors to check completed armor assemblies directly on the production line, catching deviations before tanks were completed. Spectrographic analysis equipment, installed at major fabrication facilities, could determine alloy composition from small samples in minutes rather than the hours required for traditional wet chemistry methods. The steel industry's response to wartime armor demands illustrated American industrial flexibility. Before the war, these companies had produced structural steel for buildings, sheet steel for automobiles, and specialty alloys for various commercial applications. Within months of Pearl Harbor, they had retooled production lines, trained metallurgists in armor specifications, and begun delivering high-performance military steel at unprecedented volumes. Republic Steel's Massillon plant alone produced thousands of tons of armor plate monthly by mid-1943. The facility operated continuously, with 3 shifts covering 24 hours daily. Workers, many of them women who had entered industrial employment for the first time, learned to operate rolling mills, heat treatment furnaces, and inspection equipment. The plant's output represented just a fraction of total American armor production, yet exceeded the entire armor plate output of some Axis nations. The transformation of American steel metallurgy during this period extended beyond armor applications. The research into high-performance alloys, heat treatment procedures, and quality control methods developed for military purposes laid groundwork for post-war advances in commercial steel production. Techniques pioneered under wartime pressure would influence everything from automotive steel to structural materials for skyscrapers in the decades following the war. By D-Day, June 6, 1944, American industry had produced thousands of Sherman tanks, incorporating the improved armor. These vehicles rolled off landing craft onto Normandy beaches, moved inland to engage German defensive positions, and began encountering the German weapons that had devastated earlier Allied armor in North Africa and Italy. The German perspective on American armor quality remained dismissive through early 1944. Intelligence assessments based on examination of Shermans captured in Tunisia and Italy characterized American armor steel as adequate but unremarkable straightforward carbon steel without the sophisticated alloying that German specifications employed. This assessment proved catastrophically wrong, but German intelligence had no way to know that American specifications had changed significantly between the tanks captured in Tunisia in 1943 and those landing in Normandy a year later. German tankers and anti-tank crews operating along the Normandy coast in June 1944 expected to face the same American armor they had encountered in previous campaigns. Their training emphasized the effectiveness of the 88mm gun and the lighter 75mm PaK-40 anti-tank gun against Sherman armor at typical combat ranges. Gunnery instructors had taught crews that frontal hits on Shermans at ranges up to 1,500 meters would achieve penetration reliably, while side shots remained effective at even greater distances. The reality they encountered proved different. American tanks that should have been knocked out with single hits sometimes continued fighting after absorbing multiple rounds. Crews reported impacts that produced dramatic visual effects, sparks, armor fragments, visible deformation, but failed to penetrate completely. Anti-tank gun crews, positioned in carefully prepared defensive positions along likely approach routes, found themselves firing multiple rounds at individual Shermans that previous experience suggested should have been destroyed with the first shot. Hauptmann Bäumer's examination of knocked-out Shermans near Villers-Bocage in mid-June 1944 represented one of the first systematic German attempts to understand why American tanks seemed more resistant to 88mm fire than previous combat experience suggested they should be. His initial field examination noted the unusual deformation patterns around impact sites' armor that absorbed energy rather than fracturing cleanly. Bäumer photographed the damage extensively, using a Leica camera to document the impact sites from multiple angles. He measured the crater depth, noting that the deformation extended deeper into the armor than he expected, but without the characteristic cracking that typically accompanied penetrations. The weld seams near the impact, which on earlier examined Shermans had shown a tendency to crack and separate under shock, remained intact. Something about this armor was fundamentally different from what German technical intelligence had documented previously. The sample Bäumer cut from the damaged Sherman required portable oxyacetylene cutting equipment and considerable effort. The armor resisted cutting more than he anticipated, the torch taking longer to penetrate than experience with previous Sherman armor suggested it should. He extracted a section approximately 10 centimeters square, careful to include the heat-affected zone near the impact site, and undamaged material for comparison. This sample, carefully packaged and labeled, was shipped back to Kummersdorf for detailed metallurgical analysis. The Battle of Villers-Bocage on June 13, 1944, illustrated both the continuing German advantages in tactical skill and the increasing difficulty of achieving quick kills on American armor. SS Obersturmführer Michael Whitman's famous ambush of British columns, which destroyed numerous Cromwell cruiser tanks and half-track vehicles, also engaged American Sherman tanks supporting the advance. Whitman's Tiger First, with its 88mm gun and thick frontal armor, possessed overwhelming technical advantages in individual combat. Yet several Shermans in the engagement survived hits that should have been catastrophic. One Sherman, later examined by American ordnance officers, showed 3 distinct impact sites where 88mm rounds had struck without achieving complete penetration. The glacis plate had deformed significantly at each impact point, and fragments had spalled from the interior surface, wounding crew members. But the armor had not failed completely, and the tank had remained mobile long enough for its crew to escape after the vehicle caught fire from a subsequent hit to the engine deck. German after-action reports from the engagement noted unusual difficulty in achieving quick kills on American armor. Unit commanders reported ammunition consumption per kill that exceeded their expectations based on previous combat in North Africa and Italy, where a single 88mm round had reliably destroyed Shermans in Tunisia. Normandy engagements sometimes required 2 or 3 hits to achieve the same result. This increase in rounds per kill had significant tactical implications. German tank and anti-tank units carried limited ammunition loads, typically between 60 and 80 rounds for tank guns, and similar quantities for towed anti-tank weapons. If each kill required additional ammunition, the effective engagement capacity of each gun decreased proportionally. A Tiger tank that might have destroyed 10 enemy tanks with its ammunition load now might achieve only 6 or 7 kills before exhausting its ready ammunition. The strategic implications extended to logistics and ammunition production. German ammunition factories, already struggling under Allied bombing and raw material shortages, could not easily increase output to compensate for higher battlefield consumption rates. Every additional round required per kill meant proportionally fewer tanks could be engaged with available ammunition stocks. For an army increasingly outnumbered and outproduced, this efficiency loss contributed to an unsustainable tactical situation. Reports from other sectors of the Normandy front confirmed Bäumer's observations. Panzer Lehr Division, one of Germany's premier armoured formations, engaged American forces extensively through late June and into July. Their after-action reports documented numerous instances where Sherman tanks survived hits that doctrine and training suggested should have achieved kills. Tank commanders noted that American armor seemed more resistant to frontal hits, forcing German crews to maneuver for flank shots or target vulnerable areas like the engine deck and turret ring. The psychological impact on German tank crews became apparent through letters and diary entries. Soldiers who had fought with confidence in their technical superiority now expressed uncertainty. If the 88mm gun, the weapon that had defined German anti-tank capability since North Africa, could not reliably destroy enemy tanks, what did that mean for their chances of survival? German crews had accepted that they would be outnumbered, that American artillery and air power would be overwhelming, but they had counted on their tanks being individually superior. The erosion of that confidence affected morale in ways that tactical training could not easily address. Similar reports accumulated from units equipped with the Panther tank. The Panther's 75mm KRK-42 gun possessed excellent armor-piercing capability, superior in many respects to the 88mm in terms of penetration at range. Yet Panther crews also reported increased difficulty achieving quick kills on American Shermans. Engagement reports documented hits at ranges where penetration should have been certain, yet targets remained operational or mobile long enough to return fire or withdraw. The German tank destroyers, including the Jagdpanzer IV and the Jagdpanther, mounted high-velocity guns in heavily armoured, low-profile chassis optimised for defensive ambush tactics. These vehicles achieved numerous successes against Allied armour through the Normandy campaign, but their crews also noted that American tanks showed improved survivability compared to earlier campaigns. Ambush engagements that should have destroyed multiple targets with rapid sequential fire sometimes resulted in fewer kills, as tanks absorbed hits without immediate catastrophic failure. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The metallurgical analysis at Kummersdorf, conducted through July and August 1944, revealed composition and microstructure that puzzled German experts. Dr. Friedrich Körber, who directed the armor testing section, personally supervised the examination of Bäumer's sample. The chemical analysis showed nickel content substantially higher than German intelligence. Believed American specifications allowed approximately 3.5%, compared to the 1.5 to 2% documented pre-war American standards. Chromium and molybdenum contents also exceeded expected values. The microstructure, examined under optical microscopy at magnifications up to 1,000 times, showed fine, uniform grain structure, with phase distributions indicating sophisticated heat treatment. The hardness values measured across the sample ranged from 280 to 310 Brinell, significantly harder than earlier Sherman armor samples in Kummersdorf's reference collection, while maintaining toughness that should have required softer steel. Dr. Kerber prepared a detailed technical report for distribution to the Army Weapons Office and the Armaments Ministry. His conclusions were sobering. The Americans had developed armor steel that matched or exceeded German specifications in key performance parameters, while apparently manufacturing it at scales that allowed installation in standard production vehicles. This represented a metallurgical achievement that German industry had not accomplished, producing high-performance armor steel in quantities sufficient to equip thousands of tanks. The report noted specific technical achievements that impressed the German analysts. The uniform grain structure throughout the plate thickness indicated precise control of rolling temperature and reduction ratios. The hardness gradient from surface to core followed an optimized curve that provided maximum penetration resistance at the face while maintaining toughness at depth. The alloy composition balanced multiple elements in ratios that suggested extensive experimental development and sophisticated understanding of steel metallurgy. What troubled Dr. Kerber most was not any single technical feature, but the evidence of systematic improvement across the entire production base. American industry had identified armor performance deficiencies, developed solutions, implemented those solutions across multiple steel mills and tank manufacturers, and delivered improved products to combat units, all within approximately 12 to 18 months. This demonstrated industrial capability and organizational effectiveness that Germany, despite its reputation for technical excellence, had not achieved. Dr. Werner Osenberg, head of the planning office in the Reich Research Council, reviewed the Kummersdorf findings in late August 1944. His memo to Armaments Minister Albert Speer acknowledged that American metallurgical capability had been substantially underestimated. The Americans had developed armor steel matching or exceeding German specifications while manufacturing it at scales Germany could not approach. Speer's response, documented in his ministry's records, expressed frustration that German intelligence had failed to detect these improvements earlier. If American armor had been enhanced significantly, what other improvements might have been implemented without German knowledge? The Americans had demonstrated capability to improve their weapons continuously while maintaining production volume, a combination that Germany found increasingly difficult to achieve as the war progressed. This admission carried profound implications. German war production strategy had assumed that technical superiority in individual weapons systems would compensate for numerical disadvantages. The Tiger tank, the Panther, the new jet aircraft, all represented attempts to achieve qualitative superiority that would offset quantitative American advantages. But if American industry could improve its products continuously, matching or exceeding German technical achievements while producing at vastly greater scale, the entire strategic calculus became untenable. German armor steel production faced increasing difficulties through late 1944. Allied bombing of steel-making facilities disrupted production schedules and damaged critical equipment. The Krupp Steelworks in Essen, Germany's premier specialty steel producer, suffered repeated raids that destroyed furnaces, rolling mills, and heat treatment facilities. Railway networks, targeted systematically by Allied air forces, made delivery of raw materials unpredictable and complicated distribution of finished armor plate to tank manufacturers. Raw material shortages compounded production difficulties. Nickel supplies, dependent largely on imports that Allied naval supremacy had cut off, dwindled to critically low levels. German armor specifications had to be modified, reducing nickel content and attempting to compensate through increased chromium and molybdenum. But these substitute alloys required more careful heat treatment and showed greater quality variation than the nickel-bearing steels they replaced. Labor shortages affected every aspect of German war production. Skilled metallurgists and steel workers had been conscripted for military service, replaced by forced laborers from occupied territories who lacked training and, in many cases, deliberately sabotaged production. Quality control degraded as experienced inspectors became scarce, and production pressure forced manufacturers to accept marginal material that would have been rejected earlier in the war. The contrast between German and American situations could not have been more stark. While German steel mills struggled under bombing, material shortages, and labor difficulties, American facilities operated at full capacity, safe from attack, with access to global raw material supplies. Where German armor quality deteriorated, American armor quality improved. The Industrial War, decided not on battlefields but in steel mills and factories, had turned decisively against Germany by autumn 1944. American metallurgists, meanwhile, continued refining their armor specifications through the latter half of 1944. Analysis of combat-damaged tanks returned from Europe provided feedback that guided further improvements. Ordnance engineers examined every penetration, documenting impact angle, projectile type, range when known, and the specific failure mode of the armor. This systematic collection of combat data allowed metallurgists to identify remaining vulnerabilities and develop targeted solutions. One significant finding involved the junction between glacis plate and hull side armor. Early improved armor specifications had focused primarily on the frontal glacis, where most hits occurred. But combat data showed that hits near weld seams, particularly at the corners where glacis met side armor, sometimes produced cracking that propagated along welds. Metallurgists responded by developing improved welding procedures and specifying additional stress relief heat treatment after welding to eliminate residual stresses that contributed to crack propagation. Another refinement addressed the armor backing the ammunition storage bins inside the hull. Fire from penetrating hits remained the leading cause of catastrophic tank loss. The secondary explosion of stored ammunition killing crews and completely destroying vehicles. Engineers developed supplementary armor panels with specialized compositions that resisted spalling when struck, reducing the shower of fragments that could detonate stored rounds even when primary armor wasn't fully penetrated. These incremental improvements, each addressing specific vulnerabilities identified through combat experience, represented exactly the kind of continuous refinement that German industry could no longer accomplish. American tanks landing in Europe in late 1944 and early 1945 incorporated dozens of modifications compared to early production vehicles, each improving survivability, reliability, or combat effectiveness in some measurable way. The improved Sherman armor contributed significantly to American tactical confidence through the late summer and autumn campaigns of 1944. Tank crews who might have hesitated to engage German armor aggressively instead fought with assurance that their vehicles offered meaningful protection. This psychological shift enabled more assertive tactics that exploited American advantages in numbers, mobility, and artillery support. The Battle of Aracourt in September 1944 demonstrated how improved armor, combined with superior tactics and training to defeat German forces despite their technical advantages in individual vehicle performance. Combat Command A of the 4th Armored Division, equipped largely with late-production Shermans incorporating the improved armor, engaged the German 113th Panzer Brigade in 11 days of intense combat. The German brigade fielded approximately 90 tanks, including 42 Panthers with their superior armor and guns. American forces, with roughly 50 Sherman tanks supported by tank destroyers and comprehensive artillery, faced numerical disadvantage in armor. Yet the Americans achieved a decisive victory, destroying approximately 86 German tanks while losing 25 Shermans. The kill ratio heavily favored the Americans despite their technical disadvantage in individual tank specifications. American Sherman crews at Aracourt benefited from multiple advantages that collectively overcame German technical superiority in armor and firepower. They had better training, with veteran crews who understood combined arms tactics. They had superior logistics, with ample ammunition, fuel, and replacement vehicles. They had overwhelming artillery support and, when weather permitted, complete air superiority. But they also had improved armor that allowed them to survive encounters long enough to exploit these other advantages. Multiple instances during the Aracourt fighting illustrated the improved armor's contribution. One Sherman, commanded by Staff Sergeant Charles Trover of the 37th Tank Battalion, took 3 hits from a Panther's 75mm gun during an engagement on September 19th. 2 rounds struck the frontal glacis at oblique angles, producing dramatic sparks and deforming the armor visibly but failing to penetrate. A third round hit the gun mantlet, penetrating the front but stopping against the internal gun mount without reaching the crew compartment. Trover's tank remained operational, returned fire, and knocked out the Panther with a shot to its thinner side armour as it attempted to reposition. Without the improved armour, Trover's Sherman would likely have been knocked out by the first or second hit, joining the casualty list rather than contributing to the successful defence. His survival and continued effectiveness represented exactly the kind of tactical advantage the armour improvements provided, not invulnerability, but sufficient protection to allow skilled crews to fight effectively, even when outgunned. German perspective on the Arras-Court battle included recognition that American armour seemed more resistant to their weapons than doctrine predicted. The 113th Panzer Brigade's after-action reports, captured after the war, noted that Panthers were achieving hits on American tanks but not always producing quick kills. Crews reported needing multiple hits to knock out Shermans that should have been destroyed with single rounds. This forced German tanks to remain exposed longer during engagements, making them vulnerable to return fire or flanking attacks. The psychological impact on German tank crews, already evident from Normandy fighting, intensified after Arras-Court. The 113th Panzer Brigade, effectively destroyed in the battle, had entered combat with factory-fresh Panthers and crews who had been trained to believe in their vehicle's superiority. Their catastrophic defeat shattered confidence throughout the German armoured forces on the Western Front. If Panthers couldn't defeat Shermans in relatively open terrain favourable to German defensive tactics, where could they succeed? The data also revealed that survival rates improved most dramatically for hits to the frontal glacis, where the improved armour's benefits were greatest. Side and rear hits showed less improvement, as these areas used thinner armour, where metallurgical enhancements provided less benefit. Top armour, designed primarily to resist artillery fragments rather than direct fire, showed minimal difference between early and late production vehicles. These patterns confirmed what metallurgists had predicted during development, that the improved alloy specifications provided maximum advantage, where armour thickness already offered baseline protection. The enhanced steel didn't make thin armour invulnerable, but it made thick armour significantly more effective. This meant that tanks properly employed in hull-down positions, or engaging at angles that presented the strongest armour, benefited most from the metallurgical improvements. The German metallurgical response to American armour improvements came too late and in too limited quantities to affect outcomes. By the time Kummersdorf completed its analysis in late summer 1944 and German steel mills began attempting to develop countermeasures, the material shortages and bombing damage had severely degraded production capability. Even had German industry been able to develop improved ammunition specifically optimized for defeating the new American armour, the tungsten and other strategic materials required for such ammunition were simply unavailable in necessary quantities. German ammunition production through late 1944 and early 1945 relied on stocks of materials acquired earlier in the war or from dwindling imports through neutral countries. Tungsten supplies, critical for armour-piercing ammunition cores, had been severely depleted. Sweden, Germany's primary remaining source, reduced exports as German defeat became increasingly certain. Domestic German tungsten production remained minimal, with limited deposits unable to meet even a fraction of military demand. The development of armour-piercing ammunition, capable of defeating improved American armour, would have required extensive testing, specification development, and then retooling of ammunition factories, a process requiring months under ideal conditions. Germany in late 1944 faced conditions far from ideal. Factories operated under constant threat of air attack, transportation networks were disrupted, and the technical expertise needed for ammunition development was scattered across collapsing fronts or lost to conscription. German tank crews in the final months of the war fought with ammunition produced months or years earlier, from specifications developed before American armour improvements were implemented. Their effectiveness against American tanks degraded as American armour improved, creating a capability gap that tactics and training could not fully overcome. Panthers that should have been able to engage Shermans confidently at range found themselves needing closer approaches, accepting greater risk to achieve hits with sufficient impact angle and velocity for penetration. The strategic lesson became increasingly clear to German commanders through the first months of 1945. Industrial capacity to continuously improve products in production, implementing enhancements without disrupting delivery schedules, provided decisive advantage. American industry refined Sherman components incrementally throughout the war, improved armor, better ammunition, upgraded fire control systems, more reliable powertrains, enhanced crew protection measures. No single improvement transformed the Sherman into a fictus, technical match for German heavy tanks, but cumulative enhancements made it increasingly effective. Meanwhile, German vehicles remained largely static in design or, more problematically, declined in quality due to production difficulties. Late-war Panthers showed numerous quality defects compared to mid-war production. Armor hardness varied inconsistently across plates due to inadequate heat treatment control. Welds showed greater defect rates as skilled welders became scarce. Mechanical components used substitute materials that wore rapidly or failed prematurely. The technical superiority that German tanks had possessed earlier in the war eroded not through design regression, but through manufacturing degradation. Post-war examination of captured German armor by American and British technical intelligence teams revealed the extent to which German armor quality had deteriorated. A Panther tank captured intact near Aachen in October 1944 and shipped to Aberdeen. Proving ground for testing showed armor with Brinell hardness ranging from 210 to 280 across different areas, and of the same plate variation that indicated inadequate temperature control during heat treatment. Earlier war Panthers tested at Aberdeen had shown more consistent hardness values around 260 to 270. The inconsistent hardness created vulnerabilities that American tankers learned to exploit. Areas of softer armor, typically near welds or at plate edges where heat treatment effects were less uniform, became preferred aiming points for experienced crews. Sherman gunners trained to target these areas, achieving penetrations against armor that should have been proof against their guns if hardness had been uniform throughout. Weld quality on late-war German tanks showed similar degradation. X-ray examination of welds on Panthers captured in early 1945 revealed porosity, incomplete fusion, and slag inclusions that would have failed quality inspection earlier in the war. These weld defects created stress concentrations that promoted crack propagation when armor was struck. Several examined Panthers showed cracks extending from impact sites along weld lines, indicating that poor welding had compromised armor integrity. By contrast, American armor production maintained consistent quality through war's end. Late 1945 Shermans incorporated all the metallurgical improvements developed over preceding years, manufactured with quality control that had improved through accumulated experience. Metallurgists at Aberdeen Proving Ground, testing armor samples from Shermans produced in March and April 1945, found hardness, uniformity, microstructure, consistency, and weld quality equal to or better than mid-war production. The final campaigns of the European War, from January through May 1945, saw American Sherman tanks advancing relentlessly into Germany, despite continuing to face technically superior German vehicles when those vehicles could be deployed with adequate fuel and ammunition. The improved armor contributed to a tactical situation where American crews felt increasingly confident engaging German armor, knowing their chances of survival had improved meaningfully, even if not dramatically. The Rhine crossings in March 1945 illustrated how accumulated American advantages, including improved armor, enabled operations that German defenses could not prevent. At Remagen, where American forces seized an intact bridge on March 7th, Sherman tanks poured across before German forces could organize effective counterattacks. Panther and Tiger tanks sent to eliminate the bridgehead engaged American armor in desperate fighting through the following days. German tankers achieved numerous hits on American armor during the Remagen fighting, but found that achieving kills required more ammunition, closer ranges, or better shot placement than their declining numbers allowed. The 9th Panzer Division, tasked with destroying the American bridgehead, reported frustration that American tanks survived hits and continued fighting. Division reports noted that ammunition resupply couldn't keep pace with consumption rates, forcing commanders to ration rounds when facing what seemed like endless numbers of American tanks. The Ruhr Pocket encirclement in April 1945 trapped over 300,000 German troops, including significant armoured forces. During the fighting to reduce this pocket, American Sherman units engaged remaining German armour in numerous small actions. Combat reports from these engagements showed patterns now familiar from months of experience. German tanks achieving hits but not always quick kills, American tanks surviving to fight longer, and eventually prevailing through numbers and sustained firepower. One engagement near Paderborn on April 1 involved the 3rd Armoured Division engaging elements of the Panzer Lehr Division. American Shermans from Combat Command B encountered approximately 15 Panthers in a meeting engagement in rolling terrain that offered limited cover. The Panthers, positioned defensively, engaged American armour at approximately 1,200 yards, achieving multiple hits in the opening moments. Sergeant James Bates, commanding a Sherman in the lead platoon, watched 2 tanks in his section take hits within seconds. Both were struck on the frontal glacis by 75mm rounds from Panthers. Both tanks showed dramatic impact effects, sparks, smoke, visible armour deformation, but neither was immediately knocked out. One Sherman lost its radio antenna, severed by fragments from the impact. The other suffered damage to external stowage, with equipment torn loose by the hit's concussion. But both tanks remained mobile with functioning main guns. The engagement continued for approximately 20 minutes as American forces manoeuvred for flank shots while calling artillery fire on German positions. Eventually, a combination of tank fire and artillery forced the Panthers to withdraw, having knocked out 3 American Shermans while losing 7 of their own tanks. The exchange ratio still favoured German technical superiority, but not to the extent that German planning assumed. More critically for strategic outcomes, American forces could replace their losses, while German forces could not. Bates later commented in his after-action debriefing that he watched rounds strike American tanks that he expected would produce catastrophic kills, only to see those tanks continue fighting. He attributed his survival and that of his crew to what he called better steel in late-war Shermans, though he had no knowledge of the specific metallurgical improvements. His intuitive assessment matched what technical analysis confirmed the armour had been improved in ways invisible to users, but evident in combat outcomes. The collapse of German resistance in April and May 1945 proceeded with shocking rapidity once German defensive lines broke. American armoured spearheads raced across Germany, encountering sporadic resistance from scattered German units that lacked fuel, ammunition, and coordination. The improved Sherman armour, developed to address serious tactical deficiencies in early war production, contributed to the overwhelming success of these final operations by ensuring that American tanks could survive encounters long enough to exploit their other advantages. The end came on May 8, 1945. With Germany's unconditional surrender. American ordnance officers, systematically examining destroyed vehicles across the European theatre, found clear evidence of improved armour performance on late-war Shermans. Tanks hit by German anti-tank weapons showed penetration patterns that confirmed metallurgical enhancements had achieved their intended effect. Armour that absorbed energy, resisted cracking, and failed less catastrophically when penetrated. The comprehensive post-war analysis, conducted through 1945 and 46, concluded that while improved armour meaningfully enhanced Sherman capabilities against German weapons, the truly decisive factors remained overwhelming numerical superiority, vastly superior logistics, complete air superiority, devastating artillery support, and more effective operational doctrine. The armour improvements hadn't won the war, but they had contributed to tactical effectiveness that allowed American advantages in other areas to determine outcomes. The metallurgists who developed the improved armour received little public recognition during or immediately after the war. Dr. Edgar Bain continued his research at U.S. Steel, publishing technical papers on steel metallurgy that influenced post-war armour development, but never discussing the classified wartime work in detail. His contributions to armour plate specifications remained classified for decades, known only to specialists within government and industry who had security clearances for such information. The engineers at Republic Steel, Carnegie, Illinois, and other facilities who implemented the new specifications returned to civilian production after the war. Their expertise, developed under wartime pressure to produce high-performance armor at unprecedented volumes, found application in post-war commercial steel production. The heat treatment techniques, quality control procedures, and alloy development methods pioneered for military purposes influenced everything from automotive steel to structural materials for buildings. The American steel industry emerged from World War II with capabilities and knowledge that positioned it for continued dominance through the early Cold War period. The metallurgical research conducted for armor applications had advanced understanding of steel behavior under extreme conditions, providing insights that benefited numerous commercial applications. The quality control systems developed to ensure consistent armor performance became models for post-war manufacturing across multiple industries. The strategic lesson about continuous product improvement influenced American military procurement philosophy for decades. The success of incrementally enhancing Sherman tanks while maintaining high production volumes demonstrated that evolutionary development of proven designs often provided better results than revolutionary new designs that required extended development time and created production disruptions. This lesson shaped American tank development through the Cold War, with designs like the M48 and M60 representing evolutionary improvements rather than radical departures. The Korean War, beginning in June 1950, provided an unexpected postscript to the Sherman armor story. American forces in Korea relied heavily on M4A3E8 Sherman tanks, the final production variant, incorporating all the improvements developed through World War II. These tanks, facing Soviet-built T-34, 85 tanks in North Korean and later Chinese service, proved their effectiveness in combat that validated the improvements made years earlier. The improved armor that had been developed primarily to counter German 88mm guns proved highly effective against the T-34, 85's 85mm gun. American Sherman crews in Korea reported that their armor provided good protection against frontal hits at typical combat ranges. The metallurgical improvements developed in 1943 and 44 continued protecting American tank crews in a different war on a different continent, testament to the enduring value of the research. Soviet examination of Sherman tanks, captured or abandoned in Korea, provided their metallurgists with insights into American armor technology. Soviet technical reports, declassified decades later, showed respect for American metallurgical achievements. Soviet armor development through the 1950s incorporated lessons learned from examining American armor steel, including alloy compositions and heat treatment procedures similar to those American metallurgists had developed during World War II. The technological competition in armor metallurgy continued through the Cold War as both American and Soviet researchers sought to develop armor capable of defeating increasingly powerful anti-tank weapons. Each generation of armor represented incremental improvements over previous designs, building on knowledge accumulated through decades of research. The foundation for this continued development had been laid during World War II, when metallurgists on both sides pushed the boundaries of what steel could achieve. Modern composite armors used in contemporary tanks represent a fundamental departure from the homogeneous steel armor of World War II. Materials like depleted uranium, ceramic inserts, and reactive armor systems provide protection through mechanisms that Bain and his colleagues never envisioned. Yet the fundamental principles they established, that armor performance depends on microstructure as much as composition, that manufacturing quality determines battlefield effectiveness, and that continuous improvement provides sustained advantage, remain relevant. The story of Sherman armor improvement represents a particular kind of wartime achievement, one that lacks the drama of battlefield heroics or the visibility of new weapons systems, but contributed substantially to strategic success. Metallurgists working in laboratories and steel mills, unknown to the public and unrecognized by most soldiers, solved technical problems that saved lives and enhanced combat effectiveness across thousands of engagements. Hauptmann Klaus Bäumer, whose examination of damaged Sherman armor in June 1944 had initiated German investigation of American improvements, survived the war, and worked in the West German steel industry during the post-war years. In an interview conducted in the 1970s, he reflected on his Normandy experience, examining American tanks. He recalled his surprise at finding armor that behaved differently than German intelligence had predicted, and his growing realization through subsequent analysis that American metallurgical capability had been seriously underestimated. Bäumer noted that German technical intelligence had focused heavily on counting enemy weapons and tracking production numbers, but had paid insufficient attention to quality improvements in existing designs. The assumption that American mass production meant inferior quality proved catastrophically wrong. American industry had demonstrated that mass production and quality improvement were not mutually exclusive, that production volume could increase while performance enhanced, and that industrial maturity mattered more than theoretical technical sophistication. The transformation of American tank crews from mid-1944 to early 1945 reflected the cumulative impact of combat experience, improved equipment, and growing confidence. Crews that landed in Normandy in June 1944 often felt apprehensive about facing German armor, aware of their technical disadvantages, and uncertain whether their Shermans could survive encounters with Panthers and Tigers. By early 1945, after months of sustained combat and progressive equipment improvements, American tankers approached engagements with confidence. This psychological shift had direct tactical consequences that extended beyond what improved armor alone could have achieved. Confident crews fought more aggressively, took calculated risks when opportunities appeared, and exploited tactical advantages. They coordinated effectively with infantry, artillery, and air support, implementing combined arms doctrine that negated German technical advantages. While improved armor didn't create this transformation by itself, its contribution to crew survivability and combat effectiveness was meaningful and appreciated by those who benefited from it. Lieutenant Samuel McDowell, whose platoon had survived engagement with Panthers at Dom-Bütgenbach during the Bulge, later wrote about his combat experiences. He described the moment when his tank absorbed 2 hits that should have knocked it out, allowing his crew to survive and continue fighting. He attributed his survival partly to luck, partly to good tactics, but also to what he called better tanks than we'd had earlier. McDowell survived the war, returned to civilian life, and carried with him an appreciation for the invisible improvements that had saved his life. Thousands of American tank crewmen had similar experiences, surviving hits that should have killed them, continuing fights that earlier Shermans couldn't have sustained, returning home because armor performed better than earlier production vehicles would have. Most never knew that metallurgists had improved their armor's steel composition and heat treatment. They simply knew that their tanks had been hit, and they had survived, and that was enough. The legacy of wartime armor development extends beyond the specific technical achievements to broader lessons about industrial capability and military effectiveness. The United States entered World War II with armor metallurgy that was adequate but not exceptional. Through systematic research, industrial cooperation, and continuous refinement of specifications and manufacturing processes, American industry developed armor that matched or exceeded that of any combatant by war's end. This achievement reflected American industrial strengths, ability to mobilize research talent, coordinate across competing companies, implement improvements at scale, and maintain quality while expanding production. Germany, despite its reputation for technical excellence and its initial advantages in armor technology, could not match this performance. German industry produced sophisticated armor steel for limited production runs, but couldn't maintain quality at high volume under wartime conditions. The degradation of German armor quality through the war's final years illustrated the fatal weakness of technical sophistication without supporting industrial depth. Advanced designs mean little if manufacturing capability cannot sustain them under pressure. The Allied victory in World War II resulted from multiple factors that collectively overwhelmed Axis capabilities. No single technical improvement or tactical innovation determined the outcome. But within the complex web of advantages that Allied forces accumulated, the improvement of Sherman armor represents a particular kind of contribution, one that enhanced effectiveness, while remaining invisible to most participants, that saved lives without dramatic gestures, and that demonstrated industrial capabilities decisive for modern warfare. The metallurgists at U.S. Steel, Republic Steel, Carnegie, Illinois, and other companies who developed improved armor specifications accomplished something remarkable. They identified technical deficiencies, developed solutions based on sophisticated understanding of materials science, implemented those solutions across an entire industrial base, and delivered improved products to combat units, all within the compressed time frame that wartime urgency demanded. Their success validated the American approach to military production, evolutionary improvement of proven designs, systematic quality enhancement, and industrial cooperation in service of military effectiveness. Dr. Edgar Bain died in 1971, having spent decades advancing steel metallurgy through research that influenced industries far beyond military applications. His obituaries noted his contributions to steel science, but mentioned wartime work only obliquely, as much of it remained classified. The specific improvements to armor steel he had helped develop stayed within restricted technical circles, known to specialists but not to the public whose security had been enhanced by his work. The story of Sherman armor improvement, declassified gradually through the decades following the war, provides insight into how modern industrial warfare is won. Battlefield heroics and tactical brilliance matter, but victory ultimately rests on industrial capacity to produce effective weapons in quantity while continuously improving their performance. The metallurgists who made each millimeter of American armor more effective, the steel workers who produced thousands of tons of high-quality armor plate, and the quality inspectors who ensured consistent performance, these individuals contributed as significantly to victory as the tank crews who fought with the equipment they produced. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.